All right, let's talk about the Stefan-Boltzmann law, which is the flux at the surface of the star. This graph here shows a solar spectrum. That's the flux that we're getting from the sun. Now, we know the equation for the luminosity, which is the area of the star times the flux at the surface of the star. So the area is 4 pi r squared. While the radius is an intuitive quantity, the flux at the stellar surface is not yet defined. To find this quantity, we use a concept from thermal and statistical physics, the Stefan-Boltzmann law of blackbody radiation. If you consider an ideal body that absorbs all incident radiation, that is a perfect absorber. Now, if only the absorption is considered, then the body would appear black in any wavelength. Therefore, it is called a black body. However, if the body is in thermal equilibrium, neither cooling down nor heating up, the same amount of energy absorbed must be re-emitted. That is, in thermal equilibrium, this body must also be a perfect emitter. The radiation emitted by a black body in thermal equilibrium is called black body radiation. Now, because black bodies are idealized bodies and only the temperature went into their considerations, we can expect that black body radiation will depend only on the temperature. The properties of black body radiation were found before quantum mechanics was understood. First empirically by Joseph Stefan and then shown by Ludwig Boltzmann through thermodynamics, the energy density of a black body radiation is proportional to the fourth power of the temperature, where U is the energy density and A is called the radiation constant. Its numerical value is about 7.5 times 10 to the minus 15 ergs per cubic centimeter per Kelvin to the fourth power. Now, recalling the definition that we found for the energy density and the mean intensity, we can equate that to the energy density now by this empirical law equal to AT to the fourth power. And for an isotropic field, we can say that the intensity is equal to the mean intensity and write that the intensity is equal to C over 4 pi times A times T to the fourth power. Now, we can also use it for an isotropic field, the flux is equal to pi times the intensity. And again, substitute that to find that the flux is equal to C times A over 4 times the temperature to the fourth power. Now we can define a constant called sigma, which is going to be equal to the speed of light times the radiation constant over 4. And based on that, write that the flux is equal to sigma T to the fourth power. And this result is known as the Stefan-Boltzmann law. And sigma is equal to the Stefan-Boltzmann constant. Its value is 5.67 times 10 to the 5 ergs per square centimeter per second per Kelvin to the fourth power. Right, pretty good. But what does it have to do with stars? Well, as it turns out, stars are really well approximated as black bodies. As showed before, this is the spectrum of the sun. This is a spectrum that is very well approximated by a black body. To understand why, let us consider what goes into the definition of a black body. It is a perfect absorber and a perfect emitter, described only by the temperature, irrespective of the material. This means that if a black body is composed of matter and radiation, the radiation and the matter must be at the same temperature. The dynamical equilibrium of matter and the thermal equilibrium of radiation combine into a state of thermodynamical equilibrium. Now, this is not as intuitive as it sounds. The air and the radiation around us are never in thermodynamical equilibrium. At daylight, if you measure the temperature of air, it will be around room temperature, about 300 Kelvin. Yet, the radiation is composed of photons that left the sun, traveled through a near vacuum for 8 minutes until entering the Earth's atmosphere and scattering their way towards your retina. They are solar photons, and we'll have a spectrum of a body at the temperature of the solar photosphere, around 5800 Kelvin. Clearly, radiation and matter are at very different temperatures at the Earth's atmosphere. Now, for black body, matter and radiation are at the same temperature. The photons are thermalized. For matter, thermalization happens when collisions relax the molecules to maximum entropy. If collisions are what set the state of equilibrium, we can expect that a necessary condition is that the mean free path of the molecules is small compared to the length scales of the system. Likewise, if radiation and matter are supposed to have the same temperature, the condition should be that the mean free path of the photons should also be small. Earth's atmosphere does not satisfy this condition. It is transparent to solar photons, which prevents their thermalization. When the mean free path of the photons is small, absorptions and re-emissions thermalize them, and the radiation field becomes Planckian. We will examine the physics of this process in more detail, also showing that stars are indeed in such conditions. The photons produced in the core of the sun have small mean free paths and only in a narrow layer close to the surface, less than 500 kilometers thick, they can escape. Thermodynamical equilibrium is a valid approximation, and we can then write the stellar flux following Stefan-Boltzmann law. Notice that also allows us to finally write the luminosity as a function of the radius and the temperature of the star. The luminosity 4 pi r squared sigma t to the fourth power.